Calculus, Lesson 3.5, Derivatives of Trigonometric Functions. We've done this before. We've shown this by graphing. So what's the derivative of sine of x? So here is sine of x. And if you plot derivative of sine of x, say right about here, the derivative is 1. Right here it's 0. Right about here it's about -1. Right about here it's 0. And you can quickly see how something like that. Derivative of sine of x is cosine of x. This opens up a whole world of additional derivative problems we can do. If you prove this algebraically, you'll need a few tools. Limit of cosine of h minus 1 over h equals 0. If you forgot, you should graph it. And sine of x plus h is sine of x cosine of h plus sine, cosine, sine, cosine of x sine of h. Hate it when I don't fit everything in. Anyway, I'll leave that for you. I'm not going to show it here. Now, the derivative of cosine of x is negative sine of x, and that negative causes problems. So don't forget it. A lot of people struggle with that. So we can do some problems now. Find the derivative of y equals x squared sine of x. And I'm doing two problems here. So I'll put a division down the middle. And just two separate problems. I didn't really draw it very well, but that'll have to do. Leave it alone. Take the derivative. Plus, take the derivative. Leave it alone. So y prime equals x squared cosine of x plus 2x sine of x. Can we simplify out an x? We could. Is there any reason to? No, not really. So, what about du dx of this? Well, put the one up top, leave it alone. Derivative of the other one is sine of x. Minus, leave the other one alone. Derivative of negative sine of x is negative cosine of x. Warned you about the negative, and then I forgot it. All over 1 minus sine of x quantity squared. Do some math. Negative sine of x plus sine squared x plus cosine squared x. 1 minus sine of x squared equals 1 minus sine of x. This, of course, is 1 over 1 minus sine of x times 1 minus sine of x equals 1 over 1 minus sine of x. Boy, I hope I got that right. Hey, look at that. I did. Cool. Never know what's going to happen in this crazy world. So, that's just an example. And notice the detail needed, so on and so on. So here's an application for simple harmonic motion. The position of a bob, and that's just a weight hanging from a spring. Pull 5 units down, and then it starts bouncing up and down. so that the spring is here and it gets pulled down and then it goes up and down, up and down. That's really it. The position is 5 cosine of t. And that's why I just drew a picture, because I need a picture. Really just think of a weight hanging from a spring. Maybe something like this from a countertop. It's right there, and we just pull it down and let it go, and it bounces and bounces. So the motion is just down, up, down, up, dot, 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 dot. Velocity is derivative of t, which is negative 5 sine of t. Acceleration is second derivative of t, is negative 5 cosine of t. And you'll notice that we can go on with that forever and ever. Yeah, that's about it. So, another great moment in calculus, we discussed jerks. A jerk is the derivative of acceleration. And when acceleration changes, that's when you feel a jerky motion. If the acceleration is constant, you're okay. You're in an airplane, it's taking off. It accelerates, and it constantly accelerates up until it gets to a cruising altitude, and then its velocity is constant. It's not accelerating. And that doesn't really cause a lot of problems. It's a very thrilling sensation. But if you were to go super fast and slow, then stop, then back, then forth, then left, then right, that's the kind of thing that gets people sick. So a jerk is going to be the third derivative of t. So if you have the acceleration, take the derivative. If you have the velocity, take the second derivative. If you have the body's position, take the third derivative. What is the jerk caused by the constant acceleration of gravity? Well, acceleration due to gravity is negative 9.8 meters per second squared. The derivative of acceleration is 0. So gravity does not make us feel a jerky motion. It's a constant. If you're falling through the air, you feel a constant pull straight down. You do not accelerate. You don't really change direction much. That's about it. What's the jerk of the harmonic motion in the problem above? Well, we had acceleration is negative 5 cosine of t. The derivative of acceleration would be 5 sine of t. So you're going down, up, or in this case, the jerk will feel a acceleration up, then down, then up, then down. And it has roughly the same amplitude as all the other ones, velocity and the acceleration and the displacement. You would not enjoy that as a person. There'd be a lot of jerkiness back and forth. So, last two, four derivatives. What's the derivative of tangent of x? And again, I'm going to let you guys do this. It's the derivative of sine of x over cosine of x. So do some math. Might want to pause the tape, and you will get secant squared x. And the derivative of cotangent x is negative cosecant. The derivative of cosecant x is negative cosecant cotangent of x. And the derivative of secant is secant x tangent of x. Yes, you have to memorize them. No other way about it. So we can do problems like find the lines that are tangent and normal to the graph. X equals 2. You could do this one by hand. It's a colossal mess. So better to do it with n derivative. When you do n derivative, you need to check that you're not screwing up in terms of taking a numerical derivative where you can't. So you have to think about that. Tangent x at 2 is fine. Great, it'll work. So n deriv of tangent of x over x comma x gives us our slope. So I'm just blasting this out now on the calculator. Make sure the calculator is in radians. And I get 2 point. Wonder if I did this correctly or not. .88. Did it wrong. See if I can steal it. Go back in and fix it. X. My bad. There it is. 3.433 for now. I'm leaving that saved in the calculator, because if I try and pull that out, I got a problem. Let me find my other point up here. The point is 2 comma tangent of 2 over 2, which is 2 comma negative 1.093. Again, I'm leaving that in my calculator. I'm saving it. So then I will put in point slope form. Y equals 3.433 x minus 2 minus 1.093. And that's an equation, but I'm going to go put it in slope intercept. Y equals 3.433 x. Now I've got to do some fancy work. Times negative 2 minus 1.093. And I get a y value of negative 7.59. Again, using my calculator, I go negative 1 divided by that slope. Get a value, and I am going to leave this one in point slope form. So that's tangent, this is perpendicular. Y equals negative 0.291. X minus 2 minus 1.093. And I'm doing a 2-second check. I'm doing all this by hand. I could do it on the computer, but it would take half of forever. And I get negative 0.51 for my y-intercept, which I look at and graph, and it's about right. So when I graph this, again, I should do this all in the calculator. I get the original tangent graph, looks something like this. Tangent x over x. The tangent line is right here, and the normal line is right here. Something like that. Alright, graph it, play with it, see what you get. And last but not least, what is the second derivative of secant of x? And all this says is we can do it a couple times. Derivative of secant x is secant x tangent of x. Second derivative is, leave it alone, secant squared x plus, leave it alone, secant x tangent of x. Little bit of algebra. I'm going to write my tangent first for no reason, then it just feels right. I could pull some stuff out of there, but I don't think it's going to make life any easier, so that's it. Lots there, but at the same time, nothing earth-shatteringly new and complicated. Happy mathing. Good luck.